Welcome to Let's Get to the Marks, going through the Combined Science Trilogy, Physics Higher Paper 1. This is from 2021. There are 6 questions, an hour and 15 minutes. Let's get into it. Okay, I recommend during these videos that you grab a scrap bit of paper, a pencil, and a calculator at the start of each question. Press pause once you can see the question, have a go at it, and then unpause, watch the walkthrough with the explanation, and check how you did. Okay, question 1. Figure 1 shows a mobile phone with its battery removed. There's the mobile phone, there's the battery removed. Let's go down and see what the rest wants to tell us. A student measured the potential difference across the battery and then put the battery into the phone. What is the equation linking current I, potential difference V, and resistance R? Tick one box. Now, you guys are lucky enough to actually have the equation sheet now, so that doesn't stop them asking these questions because you've got to look them up on the equation sheet. So V equals IR, and the way I remember this one, although if you have the equation sheet, you don't really need to remember it, but I think of it as very itchy rash. And I put a V at the top of a triangle and then IR at the bottom. And there we go. So you can do V over I equals R or V over R equals I. Next question they're going to do, the next thing they're going to do after asking a question like this is test us on the application of this. So let's try that. 1.2. The current in the electronic circuit in the mobile phone was 0.12 amps. The potential difference across the battery was 3.9 volts. Calculate the resistance of the electronic circuit in the mobile phone. So again, we just want to use this equation. I like to use triangles. I know most physics and maths teachers don't, but that's just me. V over I times R, calculate the resistance. So if I want R, what you do is you're going to have to do voltage. This is a divide line by current. So we're going to do voltage divided by current. And what we're going to find is the voltage is 3.9, or potential difference as it should be called. And the current is measured in amps and is 0.12 amps. And all you want to check here is you just want to make sure, is there any millivolts or milliamps? Is there a small m? No, there's no small m, there's no big M, there's no megavolts or megaamps, because then you've got to do a conversion. So we've got to do no conversions. We've just got to smash that in the calculator and work out what it is. Let me grab my calculator. So 3.9 divided by 0.12, we are looking, peoples, at 32.5. And that is ohms of resistance. So 32.5. And that is a lovely 3 marks. So this might only be 2 marks nowadays, but there you go. Bish, bash, bosh. All the marks. Okay. Write down the equation that links energy, power, and time. Once again, you will have an equation sheet, so you will be able to check this out on your equation sheet. Doesn't make it a given. You still got to find the right equation. And the way I remember this one, I mean, it's not a very good way, but it's ept, literally as it says there, ept. And so what I do is E would go at the top of my triangle, and I'd have P and T, power and time at the bottom. That is the worst triangle ever. That looks like a C rather than an E. So ept. Yep, E equals P times T. Now, can you rearrange it another way? Yes, you could. I could have done P equals E over T, or I could say T equals E over P. Any correct rearrangement of that, they will give you the mark for. Lovely. All right, let's go down, check out this next question to question 1. 1.4. The battery was charged fully when it was put into the mobile phone. The battery discharged when the mobile phone was switched on. The average power output of the battery as it was discharged was 0.46 watts. What I say to myself as I'm going through a paper, especially a physics paper, I circle any value and I try to identify, right, what's is the unit? What's the symbol? What does this stand for? Power. So they've given us the power. Time taken to fully discharge the battery was 2,500 minutes. So that's time. You're already getting it in your head. Hey, I've got power and time, so I'm probably going to be using, especially as they gave us this equation beforehand. But yeah, it's the way to kind of work out what equation you need from your equation sheet. Calculate the energy transferred by the battery. So yes, they want energy. It's P times T. It's 3 marks. So we want to do power times time equals energy. Couple of things. We need to check the units. There's no kilowatts, megawatts, or anything like that. So I can just put my power as 0.46 W. Now I want to times it by my time. this is key. The time is in minutes. Is that the normal unit for time in physics? What's the standardized unit in GCSE physics for time? Well, the standardized unit is seconds. So we're going to have to do 2,500 times 60 because we need to have time in seconds, and it's always converted to seconds unless you're told not to, i.e. you're told to do it in minutes. So we're going to get a total of 69,000 joules. And that is how much energy was transferred by the battery as it was discharged, 69,000 joules. And that's 3 marks. So one for rearranging the equation correctly to work out the energy, i.e. power times time, and then one for the conversion of the minutes into seconds, and then of course one for the correct answer, 3 marks. Oh my good gosh, I always do that. I forget to clear my tick symbol. Okay, the mobile phone includes a sensor to monitor the temperature of the battery. Figure 2 shows the circuit symbol for a component used in the sensor. Why don't you pause the video and have a go? See if you can answer what sensor is that. Okay, so this is the symbol for a thermistor, and you need to know the symbol for lots of different circuit symbols. So make sure you revise those. They're nice and easy to put in a revision guide. You can find them in any textbook. The thermistor is used in sensing circuits. It's able to switch circuits on and off when there's a change in temperature. You've got one similar to this, but that responds to light. Of course, you guys know you have the light dependent resistor, which kind of shows 2 rays of light coming down and smashing into the resistor. So it depends on these rays of light. That's known as the LDR. This is just called the thermistor. It's really like a temperature dependent resistor, but we call it the thermistor. So that will get you a mark. Both of these are very good circuits for sensing circuits. They sense changes in the environment. Okay, 1.6, the temperature of the component in figure 2 increases. The potential difference across the component remains constant. Explain what happens to the current in the component. Well, you actually need to know a little sketch graph off by heart for both the thermistor and the light dependent resistor, the LDR, and how these sketches work. You have resistance on the side. That's the symbol for ohms, which is our unit for resistance. And then at the bottom here, I'm going to write temp. My writing's so bad, I don't want to write temperature. Anyway, as the temperature increases, what happens to the resistance? Well, as temperature increases in a thermistor, the resistance goes down. Now, you could change this bottom bit to light if you're dealing with an LDR, but we're dealing with a thermistor, so we're dealing with temperature. And as the temperature goes up, resistance goes down. What do you know about the relationship between resistance and current? If the resistance goes down, current is able to go up because obviously the electrons can flow more easily through the circuit with less resistance. So, and that is the relationship. They have an inverse relationship, resistance and current, and that's one of the things you should know off by heart because you'll often be tested on that relationship. So we want to say resistance decreases. So the current increases. And there we go. That's 2 marks. One for knowing the resistance decreases with increasing temperature, and so the current increases. It's a little bit how when you open your fridge door, if you open your fridge door and you leave it open for a few seconds, an alarm sounds. Beep, 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 telling you your fridge door's open. Now, how does that electric circuit know to switch on? It doesn't have a brain, but it has a thermistor. And of course, as the temperature in the fridge starts to go up, the thermistor's resistance in the alarm circuit goes down, allowing the current to increase and flow enough to sound the bell or the alarm. And so it's a clever way of having something that can sense a change in the environment and switch a circuit on. Okay. Also, maybe the fan is linked in that way, and the fan will kick in on your fridge because the temperature has gone up, and that circuit will also have a thermistor. So as the temperature goes up, the resistance drops, the current in the fan circuit increases, switching the fan on and starts pumping out the heat out the back of the fridge or whatever it does. Okay, let's move on. Okay, we're on question 2. A radioactive source emits alpha, beta, and gamma radiation. 2.1. An alpha particle is the same mass as a helium nucleus. How many times bigger is the radius of a helium atom than the radius of an alpha particle? So really what this question is asking us is telling us that an alpha particle is the size of a nucleus. So how big is the helium atom compared to an alpha particle? Well, it's really saying how big is a helium atom to the nucleus? And what we found out is that Rutherford, when he carried out his alpha scattering experiment, only 1 in 10,000 of the alpha particles deflected back. And that told us that there was a solid, small, dense nucleus in the middle of the atom, and that it was 10,000 times smaller than the overall size of the atom. So the answer is an atom is 10,000 times bigger than the nucleus. Well, a helium atom is 10,000 times bigger than a helium nucleus. And as a helium nucleus is the same as an alpha particle, we can say the helium atom is 10,000 times bigger than the alpha particle. And there we go. What a long explanation that was. Bum, bum, bum. 2.2. Alpha particles can ionize atoms in the air. What happens to an atom when it is ionized by an alpha particle? So essentially, what they're saying is an alpha particle can smash into an atom. Okay. And here's my incredible drawing of an atom. These weird little squiggles are electrons. My alpha particle bashes into the atom. What's going to happen? One of these electrons is going to get knocked off, and hence it's going to become an ion, and it's going to become a positive ion. So let's see if we can answer this question. A neutron in the atom becomes a proton. The atom becomes a positive ion. Bosh. The atom gains a neutron. The atom gains a proton. The atom loses an electron. Absolutely. The alpha particle is colliding with the atom, and the alpha particle in that collision, it shakes the atom, and the atom loses one of its electrons. Would have been better if I'd drawn them as E minus rather than X, but never mind. And that'll get us our 2 marks. Oh my gosh, I've done the tick thing again. 2.3. A spark detector is a device that can be used to detect alpha radiation. A spark detector works by alpha particles ionizing atoms in the air near a wire mesh. A large potential difference creates a spark when the air near the wire mesh is ionized. Suggest why a spark detector cannot detect beta radiation. The problem with beta radiation is that it is not as heavily ionizing as alpha, and there's a reason for that. Alpha particles, which we can represent with a 4 or a 2, or we can represent alpha particles like this, 4 and 2. In AQA, we don't focus too much on their positive charge, but they do have a 2 plus charge. But we can see that the mass number is 4 for an alpha particle. Both these symbols represent an alpha particle. If we do a beta particle, which we can represent with 0 and -1, or we can represent it like this, 0, -1. There are options for representing a beta particle. We can see that a beta particle doesn't have a lot of mass. It's so negligible that we give it a 0 for its mass. So beta particles, when they collide with atoms, are much less likely to knock electrons off and ionize atoms. So we say that beta particles are only weakly ionizing. That's not to say that they don't cause damage and they don't ionize atoms and they're not potentially a source of causing cancer or mutations and things like that to your DNA, but they are weakly ionizing for the reasons I've expressed there. Okay, let's move on. 2.4. A teacher wants to demonstrate the radioactive a teacher wants to demonstrate that the radioactive source emits alpha, beta, and gamma radiation. Figure 3 shows the equipment the teacher has. They have a 3mm thick aluminium sheet, a thin sheet of paper, a radiation detector, a radioactive source in a holder, and the count rate meter. Describe a method the teacher could use for 6 marks. Woo! Okay, let's shrink this down so I've got a bit more room to write, and then I'll go through this. Okay, so what do we want to do here? Describe a method the teacher could use. The teacher wants to demonstrate the radioactive source emits alpha, beta, and gamma. So what we first of all want to do is just do the radioactive source, aim it at the detector, and find out how much radiation is coming out of that radioactive source. So place radioactive source next to detector and measure the kind of count rate. So we want to work out how much radiation or get a measurement of the radiation coming out of the source. So after that, place the thin paper in between the detector and the radioactive source at a set distance. I don't know. We might say, let's do 5 centimeters each time here. So we're going to do 5 centimeters, right? So now what we want to do is compare the two readings. If the count rate has gone down quite a lot, whoopsie, quite a lot when the paper is in front, then the source is releasing or decaying or is undergoing, I don't know, alpha decay. Or you could say it's releasing alpha radiation. Why? Because alpha, as you know, gets blocked by paper. It has very low penetration, so it's blocked by paper. So I might want to put because alpha is blocked by paper or is absorbed by paper, it has low penetration. So it has low penetration. So alpha has low penetration, although it's the most ionizing. So if you put the paper in front, we get a sudden decrease in the count rate. So imagine we start off just with the detector and the radioactive source, and the radioactive source is giving that out, and that says 1,000. Now, when I put the paper in between, if that drops to like 500, I know, whoa, it was giving out alpha radiation because it got blocked. However, if it doesn't get reduced, then it's not giving out alpha radiation. So I'm going to have to write in white on the side here because I've kind of run out of room. So I want to say like if the count rate does not decrease, then it is not releasing alpha radiation or alpha particles. Okay, so there we go. Lovely jubbly. Now what I want to do is test if it's giving out beta. So next, replace the paper with the aluminium sheet, or if I'm an American, the aluminum sheet, not the aluminium. So, and take the count rate. So now we're going to put the aluminium sheet in between like this. So we're taking this and putting it here, and we're going to measure the count rate. Once again, if it started at 1,000, if we just make that up and then it drops to 600, we know, oh, what type of radiation is being given out? Well, it's going to be beta because beta can't get through aluminium. So next, replace the paper with the aluminium sheet and take the count rate. If it has decreased, then beta particles are being absorbed. So beta radiation is being emitted by the source. So that's the way to find out if beta is being emitted by the source. And what we can say there is, however, if the count rate does not go down at all, then the source must be emitting gamma, as this has high penetration, only stopped by thick lead. So it's only stopped by thick concrete or thick lead. So we know that if I then put the aluminium there, and guess what? Let's say I put the aluminium there and the count rate doesn't change at all, or it just goes down to like 990 or something, then we know that whatever is coming out the radioactive source can get through aluminium to the detector, and that means it's got to be gamma. That's the only other one it can be. Now, we should also say, I must say that I've run out of room, so I'm not going to write it here, but it would be good to repeat it 3 times without the paper or aluminium to make sure we have the initial count rate from the source, and then repeat it 3 times with the paper, check for anomalies, and get a mean count rate for paper, and then 3 times with the aluminium, check for anomalies, remove them before calculating a mean for the aluminium. That's going to make your results more accurate, more valid, but I kind of run out of room there to add that in. Awesome. Okay, we're on question 3. Figure 4 shows a sailing boat crossing an ocean. There is a wind turbine on the boat. Can't actually see it, but there's a wind turbine, we're led to believe, somewhere on that boat. 3.1, the wind turbine generates electricity to charge a battery that's on the boat. Name one other renewable energy resource that could be used on the boat to generate electricity. Well, look, it looks like a nice sunny day. So we could use, of course, solar power. That would be renewable. And also, there could be something in the water, right? With the waves coming past, the kinetic energy of the waves could be used. And so we could use wave power. So I'm going to go for solar power or wave power. Ah, I'm in black, aren't I? I need to go to black. There we go. Cool. I was still on white from writing on the side. Great. Let's sing down. 3.2, the boat also has a generator that burns fossil fuel. Naughty, naughty. The battery can be charged by either wind turbine or the generator. Give two reasons why this is useful. Well, if it is not windy, then fossil fuels are reliable. And I would also say that fossil fuels generate lots of energy, so can be charged quickly. So with the burning of fossil fuels, it can be charged quickly. I mean, I'd suggest you could charge at the rate you want with fossil fuels, right? Obviously, we could also say when it is windy, um, we do not have to use fossil fuels. So reduced sort of carbon footprint, that's just one thing. We could say less greenhouse gases released, saving energy. Yeah, it won't cost you as much either. So you'd save money as well. There's all sorts of reasons why using the wind would be superior to using fossil fuels. 3.3, explain one environment. Do that again. 3.3, explain one environmental impact of using fossil fuels to generate electricity. Well, I've just kind of mentioned it there in my previous answer. So it says explain one. So I need to describe one impact and I need to explain it. So I'm going to say um, global warming. That's my impact. It could warm up the planet. Um, Combustion of fossil. Here's my explanation of why it causes global warming. Combustion of fossil fuels releases greenhouse gases, e.g., CO2, which, yeah, trap infrared radiation or whatever. I'm getting a bit excited here. Infrared radiation from the sun. So yeah, I think really just saying, look, global warming caused by the greenhouse gases released from combustion of fossil fuels is definitely enough. I could have gone down the route of of fossil fuels are non-renewable. There will be less for future generations, or they take millions of years to form. So using them means there will be less for future generations. Okay, there's quite a few numbers of things we could go down there. Go down the old acid rain, impurities, sulfur impurities in the fossil fuel can release sulfur dioxide, which can cause acid rain. There we go. 3.4, the kinetic energy of the boat is 81 kilojoules. The mass of the boat is 8,000. Calculate the speed of the boat. So got to use this calculation here, and you'll find this on your equation sheet. How do we know we've got to use that? They've told us kinetic energy. There's only one equation on your equation sheet with KE, and it is going to be like this. KE equals 0.5 or half mass times velocity squared. They've asked us to calculate the velocity, calculate the speed of the boat. So I want to do KE. Well, first of all, what we can do is times each side by 2. And what that does is that gets rid of the half. That's what a lot of people like to do. Personally, I don't like to do that, but there we go. So 2 times KE over the mass equals velocity squared. Then you've got to say to yourself, well, I don't want the square of the speed. I just want the velocity. So what we're going to do to get rid of the square, I'm going to square root both sides, and that will get rid of the square. So in order to find the velocity, I need to do the square root of 2 times the kinetic energy divided by the mass. So I've got the right equation. I've rearranged it correctly. I've got at least one mark there. Now, I need to check my units. 8,000 kilograms. Well, mass is always in kilos, so that's lovely jubbly. I'm going to write 8,000 kilos there. In physics, we like to use kilograms for mass. I know in chemistry you use grams when you're doing moles, but in physics, kilograms for mass. Get that down. However, energy is measured in joules, not kilojoules. So I need to convert that to 81,000 kilojoules. Sorry, 81,000 joules by timesing by 1,000 to get rid of that K. And that's going to give us 81,000 joules. I keep saying 81,000 kilojoules. That's going to give us 81,000 joules. And remember that we're timesing it by 2. So 2 times 81,000 is 162,000. So I need to 2 times that, and that's going to give me that. And then I'm just going to do it divided by 8,000. But what have I forgotten? We need that square root. So I'm going to do 162,000 divided by 8,000. That is going to give me the square root of, I then need to square root the answer. The answer is 20.25, and I need to square root that answer. So square root answer, and I'm going to get 9 over 2, which is 4.5 meters a second. So the way the marks work out, we've already picked up two, one for the conversion, one for the correct rearrangement. Smash that in the calculator, square root that, you get 20.25, square root that, you get 4.5. Lovely. Now, you don't have to times by both sides by 2. If you check the mark scheme, they don't do that. A level, they tend to always times by 2. You can just do the kinetic energy, which would be 81,000 once you put it into joules, divided by 0.5 times 8,000, which is 4,000. You're going to get the same answer, 20.25, then square root it to get 4.5, just in case you was wondering. Okay, get to the last bit. As the boat passes over a wave, the gravitational potential energy of the boat increases by 19,600. So essentially what they're saying is our boat has gone, whoa, it's gone up a wave like that. So there it is on the wave. It now has a GPE. It's increased its GPE by 19,600 joules. The mass of the boat is still 8,000. We've been given the gravitational field strength. Calculate the change in the height of the center of the mass of the boat as it passes over the wave. So really, we just need to rearrange the GPE calculation, and you'll find this on your equation sheet. But it might not say gravitational potential energy. It might just say potential energy, but it's the same thing. And it's your height times your mass times your GFS, which is gravitational field strength. Now, if we want to find H, what we need to do is rearrange this by dividing. We need to get rid of the M in the GFS. So we're going to divide both sides. Because they're times, we're going to divide both sides by M and GFS, and we're going to get GPE over the mass times the GFS, and that is going to give us the new height, or the height gained. So the change in height, let's do it. So we have 19,600. I don't need to convert this. It's already in joules, this GPE, lovely bubbly, or lovely jubbly. 8,000 is the mass of the boat. And then I'm going to times that by the GFS, which is 9.8. And this should give us our three wonderful marks. Obviously, 19,600. I want to divide that by 8,000 times 9.8. And we're going to get a quarter. So I've got 0.25 meters. Boat's gone up 0.25 meters. There we go. And so we're going to get what we're going to get marks for here, really for rearranging this equation. That was quite choosing the right equation, I suppose rearranging the equation, smashing it all in and getting the answer. Question 4. A student determined the density of a cube made of bronze. The student used a balance to measure the mass of the bronze cube, 4.2 grams. Figure 5 shows the balance before the cube was added. Ooh, 4.2 grams, and there's nothing on it. What type of error is shown on the balance? Obviously, now if he adds his bronze cube onto the balance, he's not going to get the right reading. What do we call this type of error where it's not on zero? We call it zero error. So your balance should read 0 at the start. This is known as zero error. How could the student get a correct value for the mass of the cube from the balance? Well, really, they should zero the balance, make sure the balance reads 0. Or they could add the bronze cube and subtract or minus 4.2 grams. So once the bronze cube's on there, just remember to subtract 4.2 grams. Four point three. The student measured the length of the bronze cube using vernier calipers and then using a micrometer. Table 1 shows the results. Vernier calipers, 20.1 millimeters, micrometer, 20.14 millimeters. Complete the sentence. The results in Table 1 show that the vernier calipers and the micrometer have a different what? What is it that they're different that describes the micrometer can measure to 2 decimal places. The vernier caliper can only measure to one decimal place. What is the word used to describe the ability to measure to many decimal places? The word we're looking for here is they have a different resolution. So they have a different resolution. Okay, the micrometer has a higher resolution because it can measure to smaller intervals than the vernier calipers. Okay. Okay. The student wanted to determine the student wanted to determine the density of a bronze coin. Having trouble speaking. The student had several identical coins. The volume of each coin was very small. The student added the water to a measuring cylinder. Figure 6 shows the student reading the volume of water in the measuring cylinder. Obviously, this does not look accurate. Give 2 changes they should make to increase the accuracy of the volume measurement. So it should be fairly obvious straight away. Look at this line here. How are they supposed to tell how much water's in there? They need to keep the measuring cylinder flat, and they should be looking at it eye level to the meniscus. So we are saying keep measuring cylinder flat. And the other one would be read at eye level. Your eyes should be in line with the meniscus. And there we go. 2 marks. Let's move on. 4.5, describe how the student could use a displacement method to determine an accurate value for the volume of a single coin. So they want to determine the displacement method, or they want to use the displacement method to determine an accurate value for the volume of a single coin. So they should fill the measuring cylinder to, we're going to give a set amount, I don't know, let's say 20 centimeter cubed, then add 5 coins, let's say 5, we could say 10, then add 5 coins, read the change in volume of the water in the measuring cylinder, okay, yeah, or read the new volume, I could say, and calculate the change. So let's say read the new volume of the water in the measuring cylinder, calculate change in volume, so if it was 20 and it went up to 30, we would do 30 minus 20. There's been a change of 10 centimeter cubed. So then what we want to do is divide the change in volume by 5 to get the mean volume of a coin. Now, the reason why we didn't just add 1 coin and work out the change in volume and do it with 5 different coins or repeat it 5 times is because they already told us that the coins were very small. So each coin may only be changing the volume in the measuring cylinder by half a centimeter cubed or 1 centimeter cubed. So you need to add a whole bunch of coins to make it easier for you to read and to get less error in the measurement. In fact, I'm probably better off doing 10 coins. But there we go. So fill the measuring cylinder, add 5 coins. I'd say minimum 5, read the new volume of water, calculate the change in the volume, divide by 5, and that will give you a nice accurate volume. Old penny coins were made from a disc of bronze, shown here. New penny coins are made from a disc of a different metal. Figure 7 shows a disc of metal. Okay. Cross-sectional area. This might not be the bronze. This might be the new metal. Cross-sectional area and the thickness. Table 2 shows the information about the discs used to make each coin. I'm having trouble speaking today. Disc. The old penny had a mass of 3.6 grams, a density of 8.9, and a thickness of 0.16. The new penny had a mass of 3.6 grams, an unknown density, and a thickness of 0.17. Let's get down to the question. Oh, it's a fat 5 marker. So what we want to do here, folks, the discs used to make the old and new coins have the same cross-sectional area. So we know their cross-sectional area is the same. Calculate the value X in table 2. That's going to get us one of these 5 marks. Give your answer to 2 significant figures. That's going to get us 2 marks. The volume of a disc can be calculated using the equation volume of a disc equals cross-sectional area times thickness. And we know, and then we got the density. And we were told they have the same cross-sectional area, so we need to use that to solve this. Couple of things to bear in mind before we get this calculation done. We're calculating the density, which is X, that is missing. We've got to give the answer to 2 significant figures. That's actually going to get us all 5 marks. I don't know what I was waffling about. The volume of a disc can be calculated using the equation volume of a disc cross-sectional area times thickness. And this is key. They put it in bold black for a reason. Both discs have the same cross-sectional area. So let's go up and see how we're going to do this. Okay, we need to find density. So we're definitely going to at some point need density equals mass over volume. Now, we can see here we're not given the volume of anything, but if we can work out, we've got all the data for the old penny. If we can work out the volume of the old penny and the area of the old penny, then we can smash that in to work out the information here. Let's go through it. So first of all, we know that density is mass times volume. I need to work out the area of the old penny because the area of the new penny and old penny are the same. And what we should realize, volume is equal to the area times like the depth or the thickness. So volume is like the area times the depth. So I can rearrange this. Let's put all this data in and see what we can come up with. So I'm going to go to white so I can write on the side up here. Let's go. We've got 3.6 grams. This is for the old penny. I'm going to divide that. Now, I don't have the volume anywhere here, but I do have the thickness, and area times depth or thickness. So area times 0.16, that is equivalent to the volume, and that is equal to my density of 8.9. Now, I can rearrange this to find A, and I can do 3.6 divided by 8.9 times 0.16, and that will give me A. So let's have a go at that. So let's do that. 3.16 divided by 0.16 times 8.9, and that is going to give me A. And what is A going to equal? That is the area. It's going to equal, smash that in the calculator, that is going to equal 2.528, and that is my centimeters like squared or whatever. That's the area. Okay, so what I need to do now is realize that the new penny has the same area, and it told us that in bold in the stem of the question down below. So what I can do is set out this new equation, which is going to be 3.6 again. So this is for the new penny. So this was the old, and this is the new one. So I can now go 3.6, which is the mass. I need the volume underneath, and I know this time we don't know the density, so D is what we're trying to work out. We know the area is the same, so the volume is equal to 2.528 times the depth of the new penny, which is 0.17, and we know that that is equal to the density X. So let's smash that in the calculator and see what we come up with. So 3.6 divided by 2.528 times 0.17, and that gives me 8.376. Now, all I want to do That's density, so that's grams per centimeter cubed. Now, I think we've got 4 marks so far. So we've got 1 mark for doing this equation, working out what A is, another mark for rearranging that equation to find 2.58. We're then smashing that equation, that 2.58 in here, rearranging again to find the density. We've worked out the density. Now, that's only 4 marks. What was the 5th mark? Let's see. It did say two significant figures, wasn't it? Let's go and double check that. Was it 2 sig? Yeah, they want our density to two significant figures. So what I want to do here is say, well, 7 is bigger than 5. So I'm going to take this to 8.4 grams per centimeter cubed. And here we go. Okay, we're going on to question 5. A TENS machine uses an electrical current to relieve pain. Do you have to have known about a TENS machine in your content? No, you don't. This is one of those application questions where you apply your knowledge to a new situation. So figure 8 shows the electrodes of a TENS machine connected across an ankle. Here's figure 8. This must be the TENS machine as it's labeled there. It's got a wire and it's connected to 2 electrodes, one on the foot and one above the ankle. Let's go down and see what the question's about. The maximum power of a TENS machine is 240 millivolts. The potential difference across the battery in the TENS machine is 2.5 volts. Calculate the maximum current from the battery. Now, you do have an equation sheet and you can use that. You will need to work out what was there any data here? No data there. So I can skip down and we don't have to look at the picture anymore. The maximum power of the TENS machine. So we know they've told us we have power and you should be able to spot power from, oops, I'm on white. I need to go to black. Okay, you should be able to spot that watts is a unit of power. And then you're given volts, that's potential difference, but V on your equation sheet. So now what you need to do, and they want you to find the maximum current, which is I on your equation sheet. So really, you just need to go to your equation sheet and find the equation that links P, I, and V. And if you do that, you're going to see that power is linked to current and voltage like this. Power over current times voltage, i.e. power is equal to the current times the voltage, or power divided by voltage is equal to the current, or power divided by current is equal to the voltage. You get the idea. So now we need to just put these two numbers in. Now, if you forget to do the conversion, you're going to lose some marks. What we need to do here is make sure we can convert. Now, what you need to realize is there's a difference if they say 240 and it's a capital M, that's megawatts. So that's going to be big. That's bigger than kilowatts. Kilowatts is 1,000 watts. Mega is 1,000,000. So that would be 240 and 6 more zeros watts. But this is not a capital M. This is a little m, and that's milliwatts. So that's actually smaller than a watt. So we need to divide this by 1,000 to get into watts. So it's really important that you look at the unit the units of your data. And so here it's milliwatts. So we divide by 1,000. We're going to get 0.240 watts. Power is always in watts. We need to find the current. So we're going to divide that by 2.5. And the maximum current on our TENS machine is going to be 0.240 divided by 2.5. And that is going to give us 0.096 amps. Unusual here is that this is a 4 marker. You'd be like, why is this a 4 marker? Well, you're definitely getting 1 mark for the conversion of 240 milliwatts into 0.240 watts. You're definitely getting that. And then even if you mess that up and you just did power over voltage, that means you've rearranged and used the right equation. So that's a 2nd mark. And then the 3rd mark for the answer, I really don't know why it's 4 marks. They're just being uber duper super duper generous. So whether it's because you selected the correct equation, then you rearranged it correctly, then you did the conversion, and then you got the answer, it just seems like a serious generousness. And we ain't complaining about that, right? Right, let's go down to 5.2. Need to fit this on the screen. Figure 9 is a sketch graph showing how the potential difference across the electrodes varies with time. So here's the potential difference. The potential difference is measured in voltage. So we've got 0 there. We've got time. A student concluded that there was an alternating potential difference across the electrodes. So they think that there's an alternating potential difference. How does figure 9 show the student was not correct? So alternating current or potential difference means it goes in both directions around the circuit, and we often see this pattern. So they're trying to catch you out because you often see that pattern with alternating current or voltage. But actually what we're looking for here, this is zero. So this is the positive part of the graph and this is the negative. Now, an alternating current or voltage would actually drop down into the negative and then change direction and go positive and then negative and then positive. And we don't see that. So how we describe that this is definitely not alternating is that it is always in the positive direction. So we can just say the potential difference is always positive. Nice. Let's move on. Okay, we are on figure 10, shows a circuit the student built using a battery from the tens machine. So they've got a battery involving two cells. They have this symbol here, which you should recognize is a variable resistor. It is connected in series with a standard fixed resistor. It's got a voltmeter around it in order to measure the potential difference across the fixed resistor. And we have an ammeter in series too. Okay, the voltmeters are always in parallel, but that doesn't change the fact that it's a series circuit we're looking at. The student recorded how the current in the resistor varied with the potential difference across the resistor. So here's the potential difference, here's the current. What relationship does figure 11 show? This shows as the current increases, so does the potential difference. Now, you may be saying to yourself, why the hell does the graph look like that? Guess what? They're being cheeky once again. They're showing you the negative direction. Don't be scared about that. The graph could actually look like this, and a fixed resistor would have that relationship going that way. So if you had voltage against potential difference, you'd have your current there and your voltage there, and this would be the positive direction, and this would be the negative direction. This isn't that type. They haven't shown that part of the graph, so it can look a bit intimidating to some people. But the relationship is still, if current increases, so does the potential difference. So they're directly proportional, aren't they? Look, if I double the current, you double the potential difference. So they're directly proportional. The current is proportional to the voltage. I could say as current increases, excuse my spelling, I'm trying to type this through, so does potential difference. Here we go. That was a bit long. I still don't, I think I've got a few spelling mistakes there, guys, but just bear with, yeah. All right, nice. Let's move on. Oh, figure 5.4, figure 12 shows two more circuits in the student built using the battery from the tens machine. So that same battery, they're basically telling us it's the same battery. We've got an ammeter in series. Circuit A is a series circuit, fixed resistor, voltmeter in parallel. That doesn't affect that this is series. Circuit B, an ammeter in, yeah, an ammeter with a parallel circuit. We've got two fixed resistors in parallel to each other. Lovely jubbly. The resistors all have the same resistance. They're giving us some more clues. Compare the readings on the voltmeter and ammeter in circuit A with circuit B. So you might say, but there aren't any readings. You've got to work out what they would be like. So what we need to look at here, these all have the same resistance, these. So the voltmeter here will show the same, it's in parallel, and that means that the voltage will be the same across. Yeah, the voltage is the same in this resistor as it in that resistor, and it's the same as the battery's voltage. God, that took me a long while to get out, didn't it? And that the tens machine had a 5-volt battery. Then there's only one resistor here, so this is getting all 5 volts. Think about series. If I put another one in there, they would be shared. If they were the same resistors, they'd have 2.5 each, but we've just got one, so it's getting all 5 volts. You might say here, if this is the same 5-volt battery, doesn't that mean that the resistors are only getting 2.5 each? No. In a parallel circuit, the voltage stays the same in all the components. I could add 12 of these resistors, they would all have 5 volts. So we can make the comment about the volts is the reading on the voltmeter. Oh my gosh, spelling mistakes again. The reading on the voltmeter will be the same in circuit A and circuit B. So the readings are going to be the same everywhere for voltage here. Although in series circuits, if you increase the amount of resistors, the voltage would go down, but not in a parallel circuit. Voltage always stays the same as what it says on the battery. So lovely bubbly. Now, the next thing here is the current. What is the current going to be like? Well, when you add two branches like this, look, the current can actually split down two directions. We're reducing the resistance. So there's less resistance to the flow of current here. There's exactly double. The resistance has decreased of the whole circuit. So, and you should know with parallel, the total resistance in the circuit is less than the resistance of the individual resistor. So here they say the resistors all have the same resistance, but it doesn't mean that the circuits have the same resistance. So if this is 3 ohms and this is 3 ohms and this is 3 ohms because it says they've all got the same resistance, what we know is the total resistance in parallel will be less than 3 ohms. And so there's less resistance in this circuit, in a parallel circuit, so the current will be higher. Current, I can't spell, current is higher in circuit B than circuit A. And here we go. It's going to get us all of the marks. Oh, got an itchy eye. Right, let's move on. What have we got going on here? Question 6. Bum 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 bum. An air source heat pump transfers energy from the air outside a building to increase the temperature of the air inside the building. Figure 13 shows an air source heat pump. Okay, so we've got air outside the building, air inside the building. We've got an evaporator. We've got a pipe that runs to the outside of the building, comes back in. We've got a compressor squishing the air. Then we've got a condenser, and then we've got a decompressor and a coolant. God, that looks complicated to me. Okay. The compressor is connected to the mains electricity supply. The pipe in the heat pump contains a substance called coolant. In the evaporator, energy is transferred from the air outside the building to the liquid coolant. The temperature of the coolant increases and it evaporates. Explain what happens to the internal energy of the coolant as its temperature increases. So as the temperature of the coolant, as the coolant increases in temperature, the internal energy will increase. Internal energy, yes. So the internal energy increases as the particles in the coolant gain kinetic energy and move faster. So internal energy is made of two things. It's made of the potential energy, which is the kind of distance between the particles. As they get further apart, the internal energy increases. And the potential energy increases, but it's also made of the kinetic energy, how fast the particles are moving. Now, as we increase the temperature, we increase the internal energy because we increase the amount of kinetic energy in the particles. Um, internal internal energy is equal to the kinetic energy plus potential energy. Now, we're not increasing the potential energy here when we increase the temperature. We're just turning that heat energy into kinetic energy, and that's why the internal energy goes up. So it's that bit that increases the internal energy, the kinetic energy. Cool. God, that was a bit long-winded. 6.2, what name is given to the energy needed to change the state of the liquid coolant? So what do we call the energy that is required to change the state? So it's not the specific heat capacity. Do you remember what specific heat capacity is? Specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a mass by 1 degree. That is not what we're talking about here. What we're talking about here is like the specific latent heat, and that is the amount of energy needed to raise the needed to change the state of 1 kilogram of a material. Now, there are two specific names for specific latent heat. If we are changing the state from a solid to a liquid, we call it specific latent heat of fusion. And if we are turning a liquid to a gas, we call it the specific latent heat of vaporization. But here, they haven't specified whether we're changing the state from oh, well, they have. They said the state of the liquid coolant. So I guess we can call it the specific latent heat of vaporization. So specific latent heat of vapor, can't spell it, vaporization. Now, 6.3, what happens to the mass of the coolant as it evaporates and becomes a vapor? So just because I have a liquid where the particles are close together, if I evaporate it and now the particles, how many have I got? They've got six particles there, and the six particles are now spread out. Well, they still weigh the same. I haven't changed how many protons or neutrons are in the nucleus, so the mass is still the same. So we don't change the mass when something changes state. Let's zing down. Near the end of this paper. 6.4, the compressor increases the density and temperature of the coolant vapor inside the pipe. Explain why the pressure in the pipe increases. Told us that the pressure, that the temperature goes up. And when you increase the temperature, what are you going to increase about the particles in the coolant? What's going to happen to them when you increase the temperature? They're going to zip about faster. And when they zip about faster, they're going to slam into each other more, and we're going to end up with more collisions over an area of the pipe's walls, and that will increase the pressure because hopefully you remember that pressure is equal, and this is a good thing to remember in physics, pressure is equal to force divided by area. So if I can increase the force, I'm going to increase the pressure. And the fact that we've increased the temperature means the particles are going to collide with more force, exerting more force on the walls of on the area of the walls of the pipe, increasing the pressure. So what we want to say here is um, there are more particle collisions, and I should really put more frequent, but I didn't. I missed the chance for that. So I'm going to say per second, which is the same as saying more frequent. I could have said more frequent particle collisions, but I've explained that by saying more particle collisions per second, same thing. So greater force exerted over the area. I'm talking about the areas in like the walls of the pipe, if you get what I mean. They're colliding with each other and the walls of the pipe. Anywho, bish bash. I think we are nearly done. How many more questions? Is that it, or is there any more? There's another one. 6.5. The condenser transfers energy from the coolant to the air in the building. When the total energy input to the heat pump system is 1,560 kilojoules, the temperature of the air in the building increases from 11.6 to 22.1 degrees. The efficiency of the heat pump is 87.5%. The mass of the air inside the heat pump inside the building is 125 degrees. No, it's 125 kilograms. God, I don't even know what I'm talking about. Calculate the specific heat capacity of the air in the building. Give your answer in standard form, 6 marks. Woo! Some serious business. Right. Well, they've told us we need to calculate specific heat capacity, and you should know this equation off by heart. And if not, do not worry. You will have it on your sheet. So it's Q, which is energy, is equal to MC. I use a triangle for delta, delta T, which is just the change in temperature. It might look like this in your change in temperature might look like that, but I don't like to use that symbol. Sorry, but there we go. So Q equals mass times the specific heat capacity over delta T. So we need to rearrange that, right, to find the specific heat capacity. So what I need to do is I need to take the mass and divide both sides by the mass, divide both sides by delta T. And what I'm going to end up with is Q divided by M times delta T. And that is going to equal the specific heat capacity. Now I need to come up here and see if I have all of the bits that I need to do, because for 6 marks, this is going to be a little bit more complicated than it looks after here. Okay, so there is one little bit here. Let's set this out. So that the energy is, first point, we need joules. Q is always in joules. So I want to times that by 1,000. So if I times 1,000, I'm going to get Q, which is what the energy stands for. So times 1,000, I use a Q. Some people just write E, but that's just me. So if we times this by 1,000, we're going to add 3 zeros. So that is 1.56 million, right, joules. And then we're going to divide that by the mass, which is 125 kg. And the temperature change, what is the temp change? Delta T, that is going to be 22.1 minus 11.6. That is going to equal 10.5. And so the temperature change is 10.5. That seems still too simple. Let me see. I'm missing something. Hold on, folks. Ooh, 10.5. That looks a bit strange, that 10.5. We definitely get 1 for the rearrangement. We definitely get 1 for timesing that by 1,000 to get that. That's 2 marks. We've done that. We've worked out the temperature change, which is definitely another. That's 3 marks. This is definitely not going to be the specific heat capacity because we won't get 6 marks. I missed this, didn't I? You should always highlight. Okay, so the efficiency of the heat pump is 87.5%. So we're not going to get all of this because this is the total energy that went in to the heat pump system. But actually, useful energy, if we look at efficiency of the efficiency equation, Where am I? Where am I? Where am I? I'm over here. Okie dokie. Remember, efficiency is equal to uh, useful energy divided by input energy. Now let's just see. And if I want that as a percentage, that should be times 100. Oh, anywho. That's not, I can't even see what I'm doing here. Right. Yeah, and that should be times 100. So yeah, efficiency is the useful energy over the input energy times 100. That's coming out in black. Never mind. Well, let me just bang on. That's 87.5%. So I need to make what is 87.5% of that? Because if you do efficiency times input, you'll get the useful. So this is the input energy. It says total input energy, that, which is this. So I need to times that by 0.875 because when you're doing percentages, you use the decimal. So 0.875 times that. That is going to be 1,365,000. So not quite as much. And we're going to divide that by 125 times 10.5. And if I smash that in the calculator, make sure I put in the brackets, I am going to get 1040. Now, do we have to come up with the units ourselves? Let me just see. That might be another mark. No, they're giving us the units, joules, kilograms, C. Oh, and it says standard form in brackets. Oh, I've only just noticed that, right? Learning all these things on the fly. Okay, yeah. Oh, yeah, it said it here as well. Look, guys, this is why you should highlight. Silly Tom, didn't bother highlighting, got lazy. Right, standard form. So if we want the other marks, so we're getting 1 mark for doing the efficiency. That's 4 marks. And we've now calculated that. That's 5 marks, 1,040. What is 1,040 in standard form? So 1,040 in standard form is 1.04 times 10 to the 3. So yeah, that means like if you put in your calculator now 1.04 and times it by 1,000, the 10 to the 3 is the shorthand for writing 1,000, the standard form. So you're saying it's 1.04 times 1,000. And if you put in 1.04 times it by 1,000, you'll get 1,040. So you can see how they interchange. This is just a way of writing 1,040 in standard form. And there we go. That is the 6th mark. Bosh. Right, let's go down. Okay, 6.6. The air in the building gains 400 joules for every 100 joule of energy transferred. Okay, from the mains electricity supply to the compressor. An advertisement claims that the heat pump system has an efficiency of 400%. Explain why the advertisement is not correct. What they're saying here is that for every 100 joules of energy that comes in from the electricity, the building goes up by 400 joules. Well, that's impossible because the efficiency can't be more than that. Can't happen. You can't make energy. Remember the statement, energy cannot be created or destroyed. It can only be transferred. So we're getting 100 joules of energy transferred from the mains. Let's go and look at the diagram. We must be getting some energy from somewhere else. Where is the diagram? Here it is. So we've got air outside the building. We've got a compressor that's getting electricity supplied to it, and that is giving some of the energy to the inside of the building. But we've also got air outside the building. Remember, it said somewhere here, in the evaporator, energy is transferred from the air outside the building to the liquid coolant. So we've got energy coming here from the energy outside from the air outside the building and coming in there. So actually, we might be getting 100 joules from the compressor, but we must be getting the other 300 joules from the air outside the building. And as we know, there is energy losses. So some energy will be escaping. So it's definitely going to be lower. It has to be lower than 100%. You can't have more than 100% efficiency. That is an impossibility. So what I would say is, yeah, the advertising's false. Ooh, I'm typing in white. No good. We need to be black on white here. The yeah, the energy must be coming from, I should have said some of the energy. Let's do that. Some of the energy it must be coming from the air outside the building. So there we go. It does tell us it's being transferred to the coolant. So the energy must be coming from outside the building. It is this energy and the energy from the electricity that makes up the 400 joules. It is impossible, yes, to have greater than 100% efficiency, right? You can't get energy from nothing. If anyone had discovered how to turn 100 joules into 400 joules, get 400% efficiency, they'd be the richest person in the universe. And here we go. Guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll check you guys in the next video. The exams are coming. We need to revise, revise, revise. Let's go.
You're still here? It's over.